Okay, we start our lecture. We continue to talk about camera calibration. So just talk a little bit. So important one for the camera calibration, we try to find the parameters of intrinsic and extrinsic parameters. And if we try to solve any parameters, no matter is computer vision, machine learning, deep learning, to solve the linear combination equations, we will use vector and matrix. So it's use a homogeneous matrix. This kind of based on the homogeneous matrix, we try to solve it by optimization method. Okay. So we already talked about the camera model. So camera model, we have a world coordinate. Any object is world coordinate. We just pick up one world coordinate object, and then the other is camera. This camera model. Camera model include the camera, so the 3D camera model. Also, it will lens, and lens will so your object in 3D will project to the 3D camera and project to the image, the sensor, or this virtual image. So a 2D image. So each camera set has a 3D camera coordinate here and 2D image. But what you can see from eyes, you only can see the image. So what's the relationship between 2D image and the 3D world object, 3D world coordinate? That will include is extrinsic parameters and intrinsic parameters. So capital X, Y, Z are the world coordinates. The small x, y, z is a camera coordinate. And 3D coordinate to 3D, like a robot arm. Or 2D to 2D is a rotation and translation. So this is kind of affine transform. Affine transform has a translation, rotation, scaling, and the seal, but we forget about seal. So for the affine transform, for the extrinsic parameters, we have a rotation, translation. It's rotate. So you have two coordinates to rotate and translate. Right? Because this is a plus here. Plus meaning the independent. To this rotation translation orthonormal, orthogonal. This means they don't have a relationship. That's meaning you can either rotate first and translate, or translate first and rotate. Like this one, you can rotate to the same and align together. Or you can align, this one, align and then rotate. Okay, so that's the extrinsic parameters. But for the scaling is meaning the object is closer to you or far away from you. If it's close to you, that's meaning the object will be big. It's far away from you, it's smaller. This called kind of perspective projection. And this will affect it by scaling. Scaling is equal to the focal length, the alpha beta focal length. So this one is from 3D project to the image. From 3D project to the image, the projection is in intrinsic parameters. Each camera has its own intrinsic parameters. In the world, no camera has the same intrinsic parameters. So we need to do, for precise estimation, we need to do the calibration. Okay, so this is intrinsic parameters. So camera calibration is try to solve extrinsic parameters and the intrinsic parameters. Okay, so when we try to solve it, we'll use this. This is two two set of equation. We'll combine together to be one set. So this is the world. And after extrinsic parameter become camera coordinate here. So here will be to here, camera, small x, y, z, and then projection, and this image plane. So I draw this one. So this way is that this world and to camera have a rotation translation. And from camera, we do the intrinsic parameters, we do the projection. And this one is project on the camera sensor. And this one has no distortion. But what you can see, the image, because the lens, camera lens has distortion. Okay, so because of lens, so we have a distortion. So this is what you can see here. So when we try to recover from 2D image to 3D, the real object, 2D to 3D, what we will do, we will go this path. So we need to do the distortion, recover distortion parameters. We need to do the 2D, we project to 3D, and 3D do the rotation translation to the real object. Okay, so our purpose for the calibration is try to recover or try to calculate all extrinsic, intrinsic, and distortion parameters. So finally, in this equation, this is not homogeneous matrix. Homogeneous matrix only AX equal to B. But let's have two matrices. It's not homogeneous. Homogeneous has only one matrix, this one. And this either vector, sometimes it's vector, sometimes it's a matrix. And if there's matrix, this should be matrix. Okay. But here, the A will be only one matrix called homogeneous matrix. Okay, so will become this one. Okay, so this one is meaning it's from here. You 3 by 3 and 3 by 4 become 3 by 4 homogeneous matrix. So this will be here. And this is your world coordinate, this image coordinate. So we tried our purpose. We will solve homogeneous matrix first. After we solve the homogeneous matrix, we will try to solve intrinsic and extrinsic parameters, that's calibration. So this equation is important. So this one is ground truth. In our case, we use chessboard. So the corner points of chessboard is this one, 2D image. The chessboard on 2D image is this. So this is ground truth. And this P prime is a P prime equal to both matrices. Okay. So that's we will talk about the calibration. So on page 11, there's a calibration procedure. So we need to prepare a pattern. In this pattern, we use this kind of chessboard. So we prepare a pattern. And pattern from front of the camera, we need to take our experience is take about 20 times. You have a chessboard into front of camera. Even though like my notebook, this camera still can do the calibration. So I do the calibration this way. Suppose this is a chessboard. So I do the calibration. Take 20 images. Okay. And then the first step, we will use OpenCV. They will provide you the corner detection function. In OpenCV, I provide to you. OpenCV, they already have all the source code. And one example tell you how to do the calibration. They've already provided to you. So just use it. Okay. So we'll detect the corner. So the corner points actually is meaning you will know ground truth here. corner points here. 2D coordinate, because that's an image coordinate. And after you have collect this ground truth, corner points, and we'll start to do, first of all, we will try to calculate the intrinsic parameters use and extrinsic, first step, we will try to solve the find intrinsic parameters, and then extrinsic parameters use closed form solution. After that, we'll solve the distortion parameters use pseudo inverse. So this one. And because closed form solution and the pseudo inverse is the first derivative, first order calculation. But in like a deep learning, because in our most of the case, the curve is 2 degree. Okay, also I say it's like the deep learning, the example or the loss function. This is loss function. The sum of square difference loss function, because usually the curve is like this way, and we try to solve the global minima. So for the first order, this give you the initial position of the answer. Okay, so that's not good enough. This one only can give you the local minima. So we try to use the second order to solve, because this is second order. We use the second order to solve, to find the global minima. And in this case, usually we solve this kind of equation. There's only two kind, usually two kind of two order optimization method. One we call Levenberger-Marquardt LM. The second is expected maximization. There's two. I think I talked to you about both optimization method before. I think we will, I forget here. Yeah. Page 14. Yeah. This is page 11 is talk about procedure. And we try to solve this one, and we'll use LM method. The LM method, we call Levenberger-Marquardt. It's OpenCV provided to you. We just use it. Okay, this is second order optimization method, so you can find the global minima. And page 14, I do this one for you. This optimization method. So when AX equal for the homogeneous matrix, when AX equal to 0, this kind we call closed form solution. For closed form solution, when we try to solve A, we know X given the input X, we try to solve A. In this kind of process, usually we find a covariance matrix first, and then we do SVD become UW, because it's a symmetric UWUT. So U and U, this both the original UWVT, but it's a symmetric, so it's a U. Okay, so based on this one, because our solution is equal to, see this one, because X is input data has value. So that's meaning because it's equal to 0, that's meaning we should have one solution for the X to be equal 0. That's meaning if we do this one, and we'll use SVD become UWVT, and one solution for this one becomes 0, is meaning we will try to find the eigenvalue. Try to find the one eigenvalue close to the 0. This corresponding eigenvector is your answer, because we try to let this one equal to 0, because X is input data. Input data has value. It's not equal to 0. So they must, with our purpose, we try to let A, when A to be 0. So we do A become UW. Okay, so we are trying to have one W value become as eigenvalue become 0. So we'll get a 0 result. So this eigenvalue corresponding to the eigenvector, the vector will be your answer. Okay, it's called closed form solution. Second one, if ax equal to b, b is not equal to 0, how can we solve a or solve x? Either way, my example probably not good. I solve x, so a pseudo inverse is here. This one. Pseudo inverse is meaning you do a prime, a transpose, because actually we try to inverse a to b, but a has no inverse, so we do the at. So at times a, and they have inverse. Okay, so we do at times a transpose a and come here. So this will become x become at times a and inverse and times b times at. So like this way. So this become k become x, d become a, d become b. Okay, pseudo inverse. Okay, but this 1 and 2, these both are not good enough. That's because both are first order. It's only for local minima. So because our equation is second order, so we need to do the second order derivative. So we use the LM method. So this is the nonlinear approach. So we can, based on LM method, we can solve the global minima for the parameters. So what kind of situation we will use LM? What kind of situation we will use EM? Both are second order optimization method. EM is mean E is expected, M is maximal likelihood maximization. So E expected usually is the average value. Okay. So both method, if you have ground truth B, you know B. Okay. And you try to estimate B prime equal to AX. So you try to solve A or X, you know if a ground truth. In this kind of situation, we use the LM. If you don't have a ground truth, that's like unsupervised learning. You don't have a ground truth. Like this one, you don't have a ground truth. That means you need to do predict, and then you should use expected maximization. Okay. And finally, the other additional one is the Lagrange approach. And right now, in deep learning, okay, they for 1, 2, 3 deep learning use the gradient descent to solve it. But gradient descent need to do iteration, a lot of iteration, many iteration to approximate the results. So 1, 2, 3 in machine learning, or they use the 1, 2, 3, but in deep learning, because they have a lot huge parameters, it's not, you cannot solve by this one because this is not do too much iteration. So we need to, in the deep learning, okay, we use the gradient descent. So we have a many times epoch to do approach. But since year 2019, so these 3 years, people start to include one more constraint here. And this is parameter weighting. Weighting is meaning which one is important. If weighting is a smaller, suppose 0.2 and here is 0.8, and this is more important. If this is a higher and this become important, and we include one constraint, the constraint is important. They can solve this one the same can use a gradient descent, and this constraint can delete some noise or delete we call outlier. Outliers mean those data is not good. You can delete it. But if you don't use this one, just use the square term. Okay, you're affected by the noise. Okay, so then now people start to work on this approach. Okay, so we continue. So this is chessboard. Okay, so we are based on the chessboard. We will do the calibration. So we start from page 20. Start from page 20 for calibration. Okay. Again, show you. Okay, so support with chessboard, and this we use the corner detection. So this is ground truth. Those points, remember, not from outside point. No, because this is unstable. So they use inside point. This one. So front of camera, they will actually this is not a good way. They did not show will do that this way, this one. Don't do the continue. He do the long way. And the other thing is that this plane should be do the large angle, large pose. Don't do small pose. Small pose is not useful. Okay, and your homework will be this one. One of your homework, because this is very important. So that you detect a corner. So based on the corner become your ground truth. So after you the ground truth, you solve the intrinsic extrinsic parameters, distortion parameters, and you can recover back to here. So this camera coordinate, this camera here. And this is the result. That's meaning what? Meaning if I can estimate your camera position. If your image, suppose your image, I don't know your position. Okay. And you take one image, one photo, and inside your photo, suppose like my case, if we have some corner behind me, I can based on these 4 points, I can calculate, I can find your extrinsic parameters, I can find your intrinsic parameters, and then I can predict you take the position, you take the photo， 就是说如果我后面如果有这种属于这种有这种角落的东西哈，有这种角落的东西在我后面，那这样的我可以根据这4点，或是更多的棋盘格的点，我可以估出你拍这张相片的位置，可以逆回来。我只要背后有这种点的话，我就可以把它逆回来。那这个就是做 AR 的东西。AR， 你真的在做很多 AR 的 APP for the AR APP， they need to find some points. So if they can find the corner points, the plane， 一定要 plane 啊，一定要 plane。那我现在就教你这些，为什么他要这样做？这就是 calibration. So when you take the photo, inside the photo has any plane, but the plane basically the best plane is the ground. 就是通常我们把这个 plane 当成你的 ground， 就是你的那个地。那 when you do the AR, we need to have a ground. 我们要 ground 才办法在上面做事情。这好像有一个 video。就这个。This is a good example. I will teach you this one. Okay. So this is the ground. So before this one, okay, he detected this one, detect chessboard. After detect, or they it just detect the four corners. Okay. So when we do the AR, the important thing is this will be your ground, and then any object just stand on the ground. So like this way. See, so this is not real. This is virtual thing. So when you see the screen, you can see this one. So in the AR, we need a ground, and the ground is your chessboard. Okay, or your ground when you like this. Suppose this building. This is a building, and you have a building always has a corner, right? So suppose this is a building, and then building is a vertical, okay, to the ground. So this is a building. You'll find the ground will be here. Suppose this is a building here, and you know the photo have the building, so the ground will be here. Even though you did not see the ground or just see a little bit of ground, based on these 4 points, and you have you have a normal direction. This is your normal direction. So the other normal direction here. So this will be your ground will be here. So it will be your normal direction. And both normal direction will be 90, this one. Normal direction of the building and normal direction of the ground. So both normal direction will be 90-degree difference. Okay. So the same, so you can find the ground. So this is AR. So see, in this case, they don't have ground, and you will float. The virtual thing will float in the air. Oh, that's weird. Okay. So calibration is kind of all the calibration. It's important also. Camera calibration is not only important for 3D to 2D to 3D. Because you have 3D, you can build a model, and then that will become the AR. Okay, so calibration is important for the AR. See, so all the AR things. So AI, I think AI is fun. It's fun to play, and I will teach you a little bit the AR in your homework. Okay. This is the other one. This is not real. Okay. So this one is not real. And this cubes is also not real. So we can play like this one. You can see on the screen and play like this one. So you see the death, right? This is a death. The background, foreground, and unreal. So we can do that. This not difficult. That use RGBD camera. Okay. Back to here. So we continue the lecture last week. So we have this one. Okay. And we try to solve intrinsic and extrinsic parameters. Continue. So this is a UV here. UV, this is a corner points. You know the corner points. This 2D image, you know. The 3D object, 3D, the chessboard, you also know because the chessboard is you design or we download from the internet. We design. They design, but we use it. What I mean design this one. This one, we know this corner, and between two corners is 2 centimeters. But sometimes 1 centimeter is fine. Just you need to know. And how many points we also know. Okay. So in this case, we know the 3D things. So this is a in 3D. Okay. And 3D, this is the position is centimeter. And this is the image. Image is a pixel. The unit is pixel. Okay. So first one, this orange, you know what? First one, because it's the plane. The plane is meaning the z, they don't have a depth. So the z will become 0. Z value will become 0. Okay. So z is 0. We come here. So because z without depth, so it's 0. So that means R3 is equal to 0. That means z, this one. Z is this R3. R3. Because each time this one times this one, and this will be 0, right? For the multiplication, 相乘, this one times this one, so R11 times X, so R13 times Z, because Z equal to 0, so R13 will be 0, no value. This one times this one, so R23 times Z is 0, so this term is 0. So you'll find this is 3 by 4. Up to here, okay, become 3 by 3 and 3 by 1. So we can delete these 3 parameters. That's better. So our matrix become this one. And this H is homogeneous matrix. It include A intrinsic R1, R2T extrinsic parameters. So H become H1, H2, H3. This one is 3 by 3 because each H is a vector. So it becomes 3 by 3. And our purpose will try to solve H. Continue. So become this one. Come here. So our purpose, we know 3DX, we know 2D image, corner points, UV, we try to solve H. And in this one, we will find out like this homogeneous matrix and become this one. Okay, but because we use mean square difference. Sum of square difference. So this is m minus n head. M is 2D, this one. M head is this one. M head is this one. This one equal to here. I say again, we have a homogeneous matrix here. And homogeneous can become equation. Equation can become homogeneous matrix. So become this one. But in reality, because this homogeneous matrix, the last term is a denominator term. 在这 homogeneous matrix 的第三个 term 是分母的 term。为什么？因为我们从 homogeneous matrix 这是分析给你听的啊。homogeneous 把它变成原来 equation 就变成这样子。So this one, the equation actually equal to this one. So both are the same, but the format is different. This is the equation format, is homogeneous format. And based on this one, because we know the UV, this corner on image plane, okay, we know M and the 3D, the chessboard coordinate is all the coordinate. We try to solve H. Okay, so this one is become M head. So that means M is corner point, 2D corner points. So M is ground truth. We take this one. From image, you know you can corner detection, you know this one. Based on the 0, 0 here. Because this is image. Okay? So you 0, 0 here. In image. But remember, in chessboard, you are 0, 0 here. Chessboard is 3D, so 0, 0, 0 is here. This object. So object coordinate, this one will be there 0, 0, 0. But sometimes the center becomes 0, 0, 0. Depends, it's the same. But for the image, you see 0, 0 is here. We put to here. So in this one, this is ground truth. this is your 3D. So this one M head is here because this estimate. So become replace this estimation result. Use this 3D information and the parameters information. Okay. So M header become this one. So become this one. So we try to the purpose we try to solve H. So from here, this one we format. Listen. Here, right? We have this one. The same or become this one. So we know from here we try to solve H. So we put H on one side. The known, there's 2D and 3D, you know. There's 2D points, 3D points, you know. So put on the other side. So this one will reformat because we try to solve H. So we will reformat to be the homogeneous matrix. But don't confuse with this one. This is from beginning. This is from beginning. From beginning. Okay. From beginning, we have this one. And this term, intrinsic, extrinsic parameter become H. So we have this format. But our purpose is try to solve H. Okay. And we have we have an input, right? And actually in here, this will be the estimation result. But our ground truth is here. So we try to do is use ground truth UV minus the estimation U. This will be U plum V plum. So what's the U plum V plum is here. So this U plum V plum, and this one become the same. This one. So we put into, remember our format, our solution we try to solve is use this one. We try to use this one to solve it. This ground truth, this estimation. So what's the estimation? Be this one. Right? This one here will become this one. So this known, this unknown. So this become Lx equal to 0. L is known, X is unknown. This one. So we will use closed form solution to solve it. Okay. This is the same. So this one here. This one equal to this one. So this one from here become this one. It's become closed form solution. So become this one. Okay. So become this one. And this one you'll find I do for you. So we try to solve H, but H is a 3x3 matrix. But in AX equal to B format, AX equal to B format, we assume this is a vector. So they will become from 3x3 matrix become 9x1. And this input, this is M is 3D XY1, 3D XY1. And this is a 2D times 3D. So you know this one. Okay. So in total format is a ALX equal to Z problems. So this will be the closed form solution. So we use closed form solution to solve it. Closed form solution is because Lx equal to 0, but we solve X. So X should not be 0. So we will try to solve the solution based on L. So L, we create the covariance matrix L transpose times L, or L times SO transpose the same, and become this one, UVW. And we try to find the eigenvalue close to the 0. That value corresponding to one eigenvector. That eigenvector is the solution for this one. So you got the answer. Okay. So based on the the non-L, you try to solve become the singular value decomposition. So if an eigenvector, eigenvalue, from the eigenvalue, many eigenvalue, closer to the zero eigenvalue, because close to the zero eigenvalue will let this one become zero. So correspond to the eigenvector. The eigenvector is your H. So you got the solution H. So we find the H. Okay, so we find the H. So the second step, after you find the H equal to intrinsic times extrinsic parameters. So we back to original one. See, this is H. H equal A times extrinsic parameters R1, rotation R1, rotation R2, and T back to here. So this is a right now become here and here. We know H. We already solve H. So we can start to solve A and R1, R2, T. So the second one is that we find in 3D, we find one important information because the rotation, one is rotation X, rotation Y. Both axes should be orthogonal, 垂直，互相垂直90度。所以 R1 and R2 should be orthogonal to this one. So orthogonal R1 inner product R2 will become 0 here. 等于0嘛，因为它两个轴是垂直的，所以 R1 inner product R2. So R1 equal to the inverse A inverse H1 times inverse H2 here. So this one becomes 0. So you have one information. The second one is because in our coordinate, each axis should be a unit vector. Any coordinate, remember any coordinate, 任何坐标，你的轴，那个轴一定是单位向量，这注意。所以我一开始就跟你讲，有个 unit vector 很重要啊，一定单位向量。那单位向量就是它的长度等于1 here, because U is R1 and R2 is unit vector. Rotation 是 rotation 那是 unit vector. 就是这个轴啊，旋转这个轴 R1 R2 嘛 ，rotation RX RY. So last time we talked about Euler angle. Okay. So should be 1 unit. So that's meaning R1 inner product R1 equal to R2 inner product R2 become this one. Is equal. So we can do the formulate. Finally become this one. So we have two equations right now. One is from the inner product. The other is from unit vector. So we shift because it's equal. So this will be in the right hand side and shift to the other side. So that's meaning this term minus this term equal to 0. And so both equations finally become 0 at the right hand side. So the same will become closed form solution. So this equal, we move H2, this one, to left hand side. So this term minus this term becomes 0. Okay. And page 27, 28, we don't care, we just skip it. Okay. And this is just that you know the original equation. Okay. We continue with page 30, from page 30. Okay, so page 30 here, this one, HBH actually is the same as page 26. If this is minus here, okay, and this term will reformulate, become here. For each term, you have HI, HJ. And okay, but so here, back to 26. So this one, right? they assume A times A become B. A times A become B because they have A times A times A here. So A times A because there is a symmetric matrix. So it's B, B, B. So become H1B, H2. H1B, H1 minus H2B, H2 equal to 0. So that's why they do here. This means H, B, H. Remember, B is AA. B is AA here. Okay, B is AA here. So those both equations become H, B, H. And then reformat. Reformat is meaning the known put one side, the unknown put the other side, become homogeneous matrix. Because this is not homogeneous matrix, so they transfer to homogeneous matrix format, become V, B. And then B is, we try to solve this one. V unknown. V, because V we know. What's the V? V is the 26. This one, you know it's H, because you so far you already solved H. So you know the H. So H, B, H2, H1. H1, B, H1 minus H2, B, H2. So B is unknown. You try to solve. B, H is intrinsic parameters. Okay. Now H is you know from previous calculation. Okay. So we the same from this format. We try to solve, reformulate, 重新排列组合，那 become B unknown B 就放在一边。HB is this one. Because B, this is symmetric. 这是对称的嘛，所以事实上这个对称的话，你事实上要解的是 you want solve is this upper triangle, but upper right 就是上半部的三角形，这几个，这 B11 B11 B1 B11 B12 B13 B1 就是这1 2 3 4 5 6，你要解这6个，因为这个是对称的，只要解6个未知数 B 就这个。But you know H, so and H times H become V， 这个 V 在这里，就 H 啊 V 在这里啊，这个 V 是你知道的 H。那这个是重新整理过了，我没有给我有推过啊，那就变成这样子，所以又变成 VB equal to 0。So this is a closed form solution. So we can solve closed form solution using eigenvector, so singular value decomposition. So we can solve B， 就把 B 解出来了。那 B 解出来 ，OK， 那我们再往下，你 B 上是 A times A。B 是 A times A， 那事实上我算过了哈，就 B equal to A transpose times A， 就是 equal to this one. So based on this, you already know B, you already know this matrix, so you can solve alpha, right? And you can solve, actually you can solve all of them. So we can solve all of them. Okay. So there's an intrinsic parameters. So each intrinsic parameters is a combination of B。 因为你现在解出 B 的嘛，那你把这个 B， 因为根据这很多联立方程式哈，这种我试过，有真的算出来就变这样子，所以任何的内部参数都是 B 组合成的这样子，就可以解出来了。那我们待会再到时间到了，我们下 we take a break 10 minutes and we'll continue to talk about so far we solve the intrinsic parameters and we'll try to solve extrinsic parameters。 好，那我们先休息10分钟，谢谢。